Okay, so question number 8 looks like it's multi-step. Consider the bromate ion BrO3 minus. Draw the complete Lewis structure. Determine the total number of electron groups or clouds surrounding the central atom. Determine the electron geometry of the groups around the central atom. Determine its molecular shape. Determine the molecular polarity, and also determine the attractive force, dipole, etc. Okay, so we have the bromate ion, which is BrO3 minus. And for part A, when we need to calculate, or when we need to draw the Lewis structure, we first need to find out the total number of valence electrons for this ion. So bromine has 7 valence electrons, and oxygen has 6, and we have 3 oxygen atoms, so we multiply that by 3. And you'll also notice that the ion has a -1 charge. So this means an additional electron needs to be added to our total electron count. And we end up with 26 valence electrons in total. Okay, so now we can start to sketch out the skeletal structure for this ion. So bromine will be our central atom. And then I'll draw 3 single bonds to each of the oxygens. And I'll make 2 of them have a double bond. Since I know these oxygens will be neutral, and the overall ion needs a negative charge, which is why I'm leaving the last oxygen to be single bonded, since it will carry that negative charge. So let's count out how many electrons I've drawn so far. So each bond contains 2 bonded atoms, so we have 10 bonding electrons, and then I'll just count out all the electrons in the lone pairs. So we only have 24 out of the 26 for this ion, so for the remaining 2 electrons, I'm going to place them as lone pairs on our bromine. Okay, so this is the Lewis structure of bromate. And for part B, we need to determine the total number of electron groups or clouds surrounding the central atom. So we have 1 lone pair and 3 bonded atoms. So therefore we have 4 electron groups, which can also be called charge clouds. Okay, so for part C, we need to determine the electron geometry of the groups around the central atom. So we know the number of charge clouds and the number of lone pairs. So if we use a VSEPR chart, then this will help us answer the remaining questions. So when we have 1 lone pair and 3 bonded atoms, this gives us a trigonal pyramid molecular shape. Okay, so that's for part D. And part C is looking for the electron geometry. So again, using our VSEPR table, we'll see that it is a tetrahedral electron geometry. So I just wrote out the molecular shape first. So we have tetragonal pyramid molecular shape and tetrahedral electron geometry. So part E is to determine the molecular polarity. So is it polar or nonpolar? So to do this, let's find out if the bromine-oxygen bond is polar or nonpolar. So to do that, we need to calculate the electronegativity difference between bromine and oxygen. So let's look up their values. So oxygen has an electronegativity value of 3.8, or 3.5, sorry. And bromine has an electronegativity value of 2.8. So the difference between the two is 0.7. So therefore we have a polar bond. And we know that because when we have a polar bond, this means that the electronegativity difference was greater than 0.4, but less than 1.69. So now that we know that the bromine-oxygen bond is polar, then we can draw dipole moments on our molecule in the direction of the oxygen. And because of the lone pair on the bromine, these dipole moments don't cancel each other out. So therefore, the bromate ion is polar, since we have a non-zero net dipole moment due to the lone pair that causes an unsymmetrical molecule. Or I'll just say unsymmetrical ion. And there's still a part F, determine the major attractive force, dipole-dipole, etc. So just to sum it up, the dipole-dipole is the main attractive force. Because of that electronegativity difference between bromine and